Have you ever wondered what truly makes everything around us solid, gives it shape, and allows it to interact? We touch a table, feel its hardness, but deep down, it's all tiny particles constantly moving and interacting. What prevents these particles from collapsing into each other, creating complex structures from what seems like empty space? Modern science has an astonishing answer: a strange and incredibly important property of fundamental particles, which we call spin. Imagine, even if a particle has no physical size to spin in the traditional sense, it still possesses a kind of intrinsic rotational motion. It's not a billiard ball spinning, but an inherent fundamental property, much like mass or electric charge. Spin, a purely quantum concept, is the key that unlocks our understanding of how our universe is built, from the smallest atoms to giant stars. It explains why matter exists, why forces interact, and why the universe isn't just a chaotic cloud of energy. Welcome to SpaceTime's Universe Journey of Discovery, where we explore the deepest mysteries of the universe. In this video, we will explore the spin of fundamental particles, the meaning of a strange property. Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us.
Spin is one of the most fundamental properties of subatomic particles, such as electrons, protons, or photons. However, don't confuse it with the rotation of a soccer ball or a planet. Fundamental particles are considered point-like, with no physical size, meaning they have no internal structure to perform a conventional physical rotation. So how can they spin? Spin is not physical rotation, but a form of intrinsic angular momentum, a purely quantum property with no direct classical counterpart. It's as if each particle was born with a certain angular momentum, a form of self-contained rotational energy inherent to its nature. It is an indispensable part of each particle's identity. This property was predicted and confirmed through complex experiments in quantum mechanics, proving it to be a physical reality with profound implications for how the universe operates. One of the strangest things about spin is that it is quantized. This means that spin cannot have just any value, but can only take on specific, discrete values. Just like a light switch can only be on or off with no in-between state, a particle's spin can only be plus 1/2, minus 1/2, plus 1, minus 1, or 0, and other multiples of 1/2 or 1 depending on the type of particle and how we measure it. This spin value is represented by a number, such as 1/2 for an electron, and its sign often relates to the direction of the spin when measured along a specific axis. This doesn't mean the particle is literally rotating in that direction, but rather that its intrinsic angular momentum is aligned along one of the allowed quantum directions. This is a fundamental difference from classical physics, where an object can rotate at any speed and in any direction. This quantization is a core characteristic of the quantum world.
Spin is the main classifying factor that divides fundamental particles into two large groups, fermions and bosons. The distinction between these two groups is not just a technical detail for physicists. It is the foundation for the existence and structure of the entire universe. Without this distinction based on spin, matter as we know it would not be able to exist stably or interact in the ways we observe. Fermions are particles with half-integer spin, such as 1/2, 3/2, 5/2, etc. Particles that make up ordinary matter, such as electrons, protons, neutrons, and quarks, are all fermions. The most prominent characteristic of fermions is that they obey the Pauli Exclusion Principle.
This principle states that no two identical fermions can occupy the same quantum state at the same time and place, even if they try to. This is extremely important for the stability of matter. Imagine if all the electrons in an atom could occupy the same lowest energy orbit. Then all atoms would collapse, becoming a dense, structureless mass. The Pauli Exclusion Principle, thanks to the half-integer spin of electrons, forces electrons to line up into different energy orbits, creating the multi-layered structure of atoms and thus the diversity of chemical elements in the periodic table. Thanks to this principle, atoms have distinct sizes and shapes, not collapsing into a single point. It is why solid objects can maintain their form and why we cannot walk through walls easily. The one-half spin of electrons is a crucial factor for the stability of matter, allowing chemical bonds to form and ultimately allowing life to develop on our planet.
In contrast to fermions are bosons, particles with integer spin, such as 0, 1, 2, etc. The most well-known bosons are the particles that mediate fundamental interactions, also known as forces. For example, photons, light particles, have spin 1, mediating the electromagnetic force responsible for light, radio, and all chemical interactions. Gluons, the particles that mediate the strong nuclear force, also have spin 1, holding quarks together to form protons and neutrons and keeping atomic nuclei stable. Bosons do not obey the Pauli Exclusion Principle. This means that many identical bosons can coexist in the same quantum state without any restrictions. This property is a prerequisite for forces to operate and propagate through space, carrying information and energy between matter particles. For instance, billions of photons can coexist in a laser beam, all in the same quantum state, creating powerful coherent light used in many technological applications. The interaction between matter, fermions, and forces, bosons, is the foundation of all physical phenomena in the universe. Electrons, fermions, are held in orbit around the nucleus by the electromagnetic force, mediated by photons, bosons. Protons and neutrons, formed from fermion quarks, are held tightly in the nucleus by the strong nuclear force, mediated by gluons, bosons. Even gravity, although not yet fully quantized in a unified theory, is believed to be mediated by gravitons, a spin 2 boson connecting celestial bodies from the smallest to the largest.
Spin also plays an important role in generating magnetic fields and magnetic phenomena. Charged particles with spin create a magnetic dipole moment, turning them into tiny magnets. This is the basis of magnetism, from everyday refrigerator magnets to the massive magnetic field protecting Earth from dangerous charged particles from the sun. Modern technologies like magnetic resonance imaging, MRI, in medicine also utilize the spin property of atomic nuclei to create detailed images inside the body. The concept of spin was first proposed in 1925 by George Uhlenbeck and Samuel Goudsmit to explain atomic spectral lines that the Bohr model and early quantum mechanics could not fully account for. Later, it was naturally and elegantly incorporated by Paul Dirac into his relativistic wave equation for the electron. Dirac's equation not only accurately predicted the electron's spin, but also foretold the existence of antimatter, one of the greatest achievements of the 20th century physics, opening a new era in the study of matter and antimatter. In modern quantum field theory, a particle's spin is not an arbitrarily added property, but rather it arises naturally and inevitably when we try to combine the principles of quantum mechanics with Einstein's special theory of relativity. The existence of spin is a logical consequence of describing particles consistently with both these pillars of modern physics. Although it may seem abstract and difficult to visualize intuitively, spin is a real physical property, accurately measurable, and profoundly influences how matter behaves at all levels.
The famous Stern-Gerlach experiment in 1922 provided crucial experimental evidence for the quantization of angular momentum, thereby indirectly confirming the concept of spin. When a beam of silver atoms passed through an inhomogeneous magnetic field, instead of being deflected in all directions as classical physics predicted, they were only split into two distinct beams. This demonstrated that the angular momentum, and thus the spin of the atom, could only have two specific orientation values, not a continuous range. The understanding of spin does not stop at individual particles. It is also the foundation for many complex and strange quantum phenomena in condensed matter physics, including superconductivity and superfluidity, where particles combine their spins to create states of matter with unique properties never seen in ordinary materials. In condensed matter physics, the arrangement of spin in magnetic materials creates desirable material properties, from computer memory to advanced sensor technologies. Spin has even been proposed as an important factor in theories of the early universe, particularly in theoretical models of dark matter and dark energy. The way particles interact through spin can provide clues about the nature of these mysterious components that dominate the universe, making up most of its energy and mass. It is a sign that the smallest properties can have the largest consequences, shaping the destiny of the entire universe. It is strange that such an abstract property serves as the foundation for the diversity and stability of the universe. Spin is not just a number. It is a profound and elegant universal rule that ensures everything doesn't collapse into a single point, that forces can transmit information effectively, and that the universe can evolve into complex structures, from gas clouds to the most sophisticated biological systems. The concept of spin is truly a testament to the surprising and profound nature of the quantum world. It challenges our intuition about how the world should work, but at the same time, it is a powerful tool for explaining what we observe in reality.
From keeping atoms from collapsing to generating electromagnetic fields, spin is an invisible property, yet possesses the power to create and sustain the entire universe. Think about it. Everything we see, touch, or feel is built from tiny particles, and their behavior is shaped by an intrinsic property that we cannot see with our naked eyes, but can measure with the most sophisticated instruments. Spin is a reminder that reality is far deeper than we can imagine, harboring subtle and powerful laws, and is one of the fundamental building blocks of the universe's design. It is a great mystery that has been partly unraveled and continues to open up new questions about the nature of reality. Spin, a strange but essential property, has shown us that the universe at its most fundamental level is neither simple nor easy to visualize. It is one of many pieces of evidence for the complexity and richness of the quantum world. But spin is just one piece in the larger picture of wonders that the universe offers. Next, we will delve deeper into even more counterintuitive phenomena, experiments on duality and multidimensional images in the universe,
where reality seems to have multiple coexisting versions and choices. Don't miss it.